Well, hello everyone, and welcome to P33. Here we're going to explore hypothesis testing, and it's actually a really exciting part of the course, and we'll try to make it all very real for you. So we have 4 tabs here. Each one is a different type of hypothesis test, and we're going to start out with one called Athens Water 1Z, where that means one sample Z test. So the Ohio EPA reports that per capita water use in a single-family home is 72 gallons per day, with standard deviation of 10 gallons. The city of Athens randomly sampled 40 homes within the city, and the results of the sample are located here. You can see them over here. At the 0.05 level of significance, 5%, is this survey enough evidence to conclude that residents of Athens use less water than the average resident of Ohio? So let's begin by framing the problem. So what we're looking for is the probability of a sample mean, meaning the city of Athens, below the population mean, meaning the national mean. And so the case, because it's below, it's going to be a one-tailed to the left. So if you think of a normal distribution, we'll be in the left tail. And the distribution is going to be a Z distribution. The reason for that is that we know the population standard deviation. It was given right here as 10 gallons. Whenever you know the population standard deviation, you have a Z distribution. Pick the function. Well, it's going to be norm.s.dist because we're going to calculate a Z-score, and then we're going to compute the probability from the Z-score. So the null hypothesis is that there's no significant difference in water use between Athens residents and the national average. And the alternative hypothesis is that Athens residents use significantly less water on average than the national average. And so what's N? N is the number of records in our sample. So we're going to count them, put equals count, and then we'll count all the sample records here. So we have 40 records in the sample. All right, now we have some descriptive statistics, and this turns out to be really important. So we have one line that's going to be the mean, and the second line is going to be the expected variability, kind of like the standard deviation line. All right, and then though the names will change. So let's start out with the population. What's the mean of the population? Well, that was given in the problem. That's 72. What's the mean of the sample? That's going to be the average of all these. And then the last question is, what's the mean of the sampling distribution of sample means? Well, if you look at this little note here, it says that the population mean is equal to the sampling distribution of sample means, mu, per the central limit theorem. So it means it's actually going to be this one. So we'll just say it equals that one. All right, expected variability. Again, we were given that in the problem for the population. It's 10 gallons. And for the sample, we'll have to calculate it using standard deviation.s. And then all of these here. So that's 17 gallons, higher variability than you see in the population. And you can actually see that here. So here's the population, has less variability, and the sample, which is fatter east to west, has higher variability. And they have different sample means, right? There's 72, and then here's the 68 for the sample. All right, now we're getting to the most important one of all, which is the sampling distribution of the sample mean. We see here that its mean is going to be at 72, but what is this distribution going to look like? Because this turns out to be super important. And it's given by the formula of sigma divided by the square root of n. So there's sigma from the population divided by the square root of n, which is 40. And that's 1.58. So now notice that as soon as we introduce that, because it's a lot skinnier than the other two flattened out even further by comparison. And this sampling distribution tells us, hey, if you took like an infinite number of samples from the population, how would they distribute? Right? And they'd be all over the place. But notice they'd be pretty close to the population mean. And it would be kind of unusual to get a sample way out here, which is where ours is. This black triangle indicates our sample, which you see right here, its value here. It would be kind of unusual to get a sample way out here close to the tail of that sampling distribution. How unusual, we're going to find out in just a minute. The important thing for you to know is that this number was necessary to decide how tight that distribution is. So this number has a special name, and it's called standard error. So it's basically the expected variability in the sampling distribution. And we're going to see that again and again and again. We're going to reuse this. In fact, it's so important that I put a little ruler underneath of it, something that kind of looks like a ruler, meaning this is our ruler to decide if we accept or reject the null hypothesis. And you'll see why. Okay, so first we take the observed difference from mu. That's equal to x bar minus mu. And then we calculate our z-score, which is the observed difference, which is this number right here, divided by the expected variability, which is this number up here. I told you this number would come back to play. And that gives a z-score of negative 2.26. All right. You can actually see that z-score down here. There's the negative 2.26 and its associated probability, which is 1.19%. That's not a real high probability. So this curve down here is the same as the blue curve up here. It's just here it's allowed to spread out because we're not showing it by contrast with the sample in the population. All right, let's get the probability of z. We already know it's 1.19 because the graph gave it to us, but we also have to learn how to calculate it. So the way that we calculate it is we use s.dist, the z-score, and then the word true. And there's the 1.2, which is the same as 1.19, rounded up. All right, our level of significance, alpha, given in the problem was 5%, so we put a 5 there. And notice as soon as we do, then this graph indicates where the 5% cutoff is. So there's alpha at 5%. The z critical value would be 1.64. And we're way down here at negative 2.26. So we're well within the rejection region. But while we see that this value is negative 1.64, how would we calculate it? We use the norm.s.inverse function, and then we put the probability. And there's the negative 1.64. That's where it came from. All right. So our conclusion is that we're going to reject the null hypothesis. We're in the rejection reason. And the reason is that the probability of observing x bar is less than alpha. 1% is less than 5%. The interpretation of that is that the data suggests that Athens residents use less water on average than the national average. Now, we're rejecting the null, and if we're wrong, what type of error would we have committed? And that's going to be a type 1 error. So whenever you reject the null, when in fact it might be true, then you have the possibility of committing a type 1 error. We don't think we did, but you should start to be familiar with those terms. Okay. Now, let's make a confidence interval. By rejecting the null, you're claiming that the sample comes from a different population, right? Not the population. So what is the mean of that population? You can't say for sure, but you can construct a confidence interval around the sample mean in which the new population mean should appear. Now, to construct that sample mean, we're going to add and subtract the absolute value of the critical value, this critical value, times the standard error, which is our ruler up here. All right, so let's go ahead and do that. So first, let's get x bar. We already calculated it above, so we don't have to do it again. We also have the original mu from above, which was this number here. All right, and we're claiming that that original mu is going to fall outside of this confidence interval if we've done everything right. So let's try. So this is equal to x bar minus the absolute value of the critical value times the standard error. Another way of thinking of that calculation that we just did is that we are 1.64 standard errors away from the mean. Right, and so we're just trying to say, well, where does that put us? What value would that be? It would be 65. All right, and then the upper bound is just the opposite. It's x bar plus, and now we're going to add the absolute value of the critical value times, again, the standard error. See how that always comes back? All right, so what we're claiming here is that the population mean for x bar, it's not the original mean. It's not the population mean we thought it was. It's going to be a population mean that's going to fall somewhere between, whose mu will fall somewhere between 65.82 and 71.03. And we're 95% confident that we'll fall into that region. All right, now let's try to understand relationships among variables. So these are all the items that came into play in this exercise: the sample size, the standard error, the z-score, the probability, and the likelihood of rejection. And let's see how they all fit together. So the sample size is called n. If n decreases, what happens? Well, here's our standard error. If n decreases, the denominator decreases, right? If your denominator gets smaller, then your numerator gets bigger by comparison. So your standard error should increase, right? So that's not a good thing, right? Sample size goes down, we're more likely to make an error. All right, so if the standard error increases, what's going to happen to the z-score? Well, this increase, that means this whole term has increased. So this whole bottom term in this division has gotten bigger. If the bottom term gets bigger, right, if your bottom term gets bigger, then your z-score decreases. Or another way, it moves towards the center, moves towards 0, because the z-scores are, the center of the distribution is 0. So that moves towards the center. And then the probability, if you're towards the center, then your probability is actually going to increase. And if your probability is high, well, then you're probably not going to reject. So your likelihood of rejection decreases. And now we can see the converse. So if the sample size increases and gets bigger, the denominator is getting bigger. So this whole term is going to actually get smaller. It's going to decrease. And the z-score then, right, once this decreases, the z-score is going to get bigger because the denominator got smaller here. So we're going to move towards the tails. And the probability in the tails is less than the probability in the middle. So it's going to decrease. And then the likelihood of rejection, if you have less probability, increases. All right, that's when we manipulate n. What if we manipulate sigma? So if sigma increases, sigma is the numerator here. So if the numerator increases, then this whole thing is going to increase. And if this whole thing increases, then that is the denominator in the next step for the z-score. So the z-score is going to decrease. decrease means move towards the center. This will be a smaller number. And the probability at the center is going to increase. The likelihood of rejection is going to decrease. But if the standard deviation decreases, so this sigma is a smaller number, then the whole fraction is going to be worth less. So that will decrease. So if this whole thing decreases, the denominator is getting smaller, so the numerator is bigger by comparison. So it gets bigger, so it moves towards the tails. And if it moves towards the tails and the probability in the tails is less, that decreases, and the likelihood of rejection increases. So it's a good way to try to understand the relationship between all the variables. And that does it for our first video. This was about one sample z-test. In the next video, we'll look at a one sample t-test. The difference between the two is that in z, you know the population standard deviation, you know this number here. In the t-test, you don't, so you have to estimate it from the sample. We'll see you in the next video.